to the morning session. I've been instructed that we've been a little lax with the timekeeping. So if I stop us much closer to the time when we're supposed to stop, it's not because I'm anal retentive. It's because I've been instructed to be this way. So this morning, Mateusz will continue.
Thank you. So yeah, the plan for today is first to continue talking about representations because we all love representations. So finish some things about finite dimensional representations. Then briefly talk about infinite dimensional representations, namely there will be just one example, the right regular representation. And then we'll use this machinery to set up duality and construct the discrete dual of a compact quantum group. So we'll do some Fourier analysis. Okay, so I'll start with these operators that Mike briefly mentioned. So we had this contragradient representation, right? UC, which somehow, it's tricky to prove that it's actually an invertible operator. And the key, somehow, operators in the proof were these operators QR and QL. So these are you take UC star UC, and then you slice it with the Haar state. This is one of them. And the other one is you do the opposite direction, right? So you do UC, UC star. Yeah, then one of them is, I don't remember which one, but one of them is called QR, one of them is called QL, and it might be the opposite convention, but never mind. So one of them is QR, one of them is QL. It might not be exactly this, but it could be the exact opposite. Okay, but what Mike showed that these things are somehow, they are intertwiners for this UC. So both QR, QL, they are like operators on this conjugate Hilbert space, right? They live on they act on the dual space. So then we can think of I think Mike denoted this by a transpose. So you get the transpose, they are like operators on the original Hilbert space. And what turns out, and this is I think the question that Vern asked, is that one of them is a morphism, so we get morphisms from U to UCC, so when we do it twice. And the other one gives a morphism so since I don't remember which one is QR, which one is QL, I will still not write which one gives a morphism from U to UCC and which one gives a morphism from UCC to U, but we get these morphisms. And what also happens is that if U is irreducible, then UCC is also reducible. And equivalent to U. But as we mentioned, somehow in general, UCC is not a unitary representation, so this is not a unitary equivalence, right? This is some sort of equivalence, and these operators were positive, so somehow we get positive morphisms here. So the point is that if U is irreducible, UCC is irreducible, so this morphism space is one-dimensional, and there exists a positive operator in this morphism space. So we can normalize it. So this is basically unique up to a scalar, and the typical normalization is the following. So there is a unique positive rho U in morphisms from U to UCC. The normalization that is typically chosen is such that trace of rho U is equal to the trace of row inverse. And somehow this number is a canonical number associated to each irreducible representation. And this is called the quantum dimension of the representation U. So for example, if UC is unitary, this is equal to the usual dimension. Right, but somehow this row U measures how badly non-unitary is the contravariant representation. And in general, this number can be strictly larger than the dimension of the Hilbert space on which U is acting. Right, so these row U operators are very important, and they will also appear in the definition of the Haar measure on the dual discrete group. So that's why I needed to introduce them. And where they also appear is the orthogonality relations. So this is something that Mike mentioned, that when we have the compact quantum group, we can look at the coefficients of finite-dimensional representations. It's a Hopf-Star algebra, and we can basically define all the maps algebraically, right? But it was not clear whether this is actually well defined, because we didn't really know whether these matrix coefficients are somehow linearly independent, so can we actually write these maps? So orthogonality relations somehow tells you that you can find an orthogonal basis among matrix coefficients. So what's the precise statement? Orthogonality relations. So U is irreducible. Then, the statement number one is that, so we choose a basis, we choose some orthogonal basis in the carrier space of U, so U is an actual matrix of coefficients, and then the formula is the following. So if you take two coefficients, so UKL, Uij star, then this gives us delta Ki rho JL over the quantum dimension of U. And then what happens if we do the opposite direction? Uij star UKL. It's delta JL. Now it's rho inverse Ki, also over the quantum dimension. So then if we choose a basis in which these row matrices are diagonal, then we can actually find an orthogonal basis maybe up to some scalars. So then you will get really a nice linearly independent set on which we can define all these maps. And then the second part of the statement is that if V is an irreducible, an irrep not equivalent to U, yes? So that's a delta. That's a delta, yes. Rho is somehow too similar to delta. That's a delta. So if V is an irreducible not equivalent to U, then its coefficients are orthogonal to the ones of U. So really, like choosing, the basis separately for each class of reducibles, so you get really an orthogonal basis on some Hilbert space, L2 of G. And what you see here is that somehow this value, when we change the order of the product, can be different, right? It depends on this row matrix quite a bit. So it means that in general, the Haar state will not be a trace. Okay, and I will not give like an actual proof of this, but I will give an idea, because you will see that our favorite tool is useful. So basically the averaging. Idea of the proof. Say like of this first formula. So look at identity tensor H of U star. So P is just some map acting on the space on which U acts. So this, as already Mike explained a couple of times, this will be an endomorphism of U. It will intertwine. This averaged operator will be an intertwiner of the representation U. So this is a morphism from U to U. But the assumption of this theory is that U is irreducible, which means that the space of endomorphisms of U is just the scalars. So what it means that it's basically a scalar. So basically this map is a functional. So, and it's a positive functional because it's positivity preserving. So basically, yeah, it's given by some sort of positive matrix with respect to the trace. So it means that there is a matrix, say sigma B of H, such that this identity tensor H U T tensor 1 U star is equal to trace sigma T times the identity. Okay, and then by some nice computation, which is not trivial, but yeah, you can find it in Sergei's book, for example, is that sigma turns out to be equal to rho U over the quantum dimension of U. And now take T equal to a matrix unit ELJ to obtain this formula. You just compute it explicitly and you get the formula. For the second formula, you get, you choose U star U, and then this sigma is something different. It involves rho U inverse. That's why you get rho U inverse here. And then the second statement, well, you replace one of the U's by V, and then you get a morphism from U to V, but they are not a pair of non-equivalent irreducibles, so this space is 0, so that's why we get all these inner products will be equal to 0. So this is the rough idea of the proof. Okay, so something that, now we want to introduce these infinite dimensional representations, and the reason is that something that, we didn't know how to prove yet is, you look at this Hofstadter algebra generated by the coefficients of finite dimensional representations. We didn't really know if this was dense in C of G. That was not clear at all, right? Because we didn't know somehow if the, say, sum of all finite dimensional irreducibles is kind of faithful. That's why we'll need this right regular representation, for which it will be somehow easy to show that it's faithful. And then this will decompose into all the finite dimensional irreducibles, and this is how we can conclude. Okay, so we need to talk a bit about infinite dimensional representations. Okay, so like, what would be our first guess? Is that the first guess is that for the definition is that we don't change anything, right? That we take U in the tensor product of B of H with C of G, or we just allow H to be infinite dimensional. But this is not really a good definition, and the issue is that basically the issue that Robin talked about at length is that this would roughly correspond to maps from G to the unitaries on H in the classical case, which are continuous in the norm topology. And this basically never happens. So what we need is somehow maps from G to U of H that are continuous with respect to one of these weaker topologies, like strong star, something like that. So we need a slightly different operator algebraic gadget here. And like the correct definition involves something called a multiplier algebra. So we take the compact operators on H, tensor with COG. So this is like this tensor product of C-star algebras, the most basic one. And then take the multiplier algebra of this. So let me maybe very briefly discuss what is the multiplier algebra. So A is a C-star algebra inside some B of H. So A is a C-star algebra. And then basically for this definition to be non-trivial, we want A to be non-unital. So just like the compact operators, I mean, they don't contain the identity. This is a non-unital C-star algebra. Okay, and then assume that somehow A acts on the whole Hilbert space, right? It's not really reduced to some proper subspace. So assume that A is non-degenerate, meaning that if you act with all operators on A, on all vectors on H, this is actually a dense subspace of H. Like for compact operators, I mean, you can move any vector to any other vector using compact operators, so you actually, you get this. And then the multiplier algebra consists of those operators, B of H, such that TA and AT belongs to A for each A in A. Maybe a quick test whether this definition is somehow understandable. So what is the multiplier algebra of the compact operators? Does anyone know? I mean, not the usual suspects. I know you know. You have a guess? Yeah, Mateusz? Yeah, B of H, right? Because basically, I mean, compact operators form an ideal, right? If you compose any bound operator with a compact operator, whichever way you go, you get a compact operator. So, and compact operators act in this non-degenerate way on H automatically with its canonical representation. So for compact operators, you get B of H. So somehow you see that if I didn't have the parentheses, like I had this, then this would be the same thing. But I really don't want to do that, and I want this, and this is maybe a slightly more mysterious object, but it corresponds really to these strongly continuous unitary representations. Maybe strong star, one of these funny topologies.
Can I ask a question or a comment? So
yes.
You started with A and B of H.
Yeah.
Did the H really matter in this definition?
No, as long as A is non-degenerate, somehow this gives you an isomorphic object. So there is also an abstract definition of multiplier algebra, which I didn't want to go into really because it would take much more time. But somehow for any non-degenerate representation, it's isomorphic to this object. Okay.
How do you see that this corresponds to the strong star?
How do we see that? Yeah, it's not obvious. I don't think. No, it's not. It's not obvious. Okay, so we will try to I will try to give you an example. So first recall that we have this thing. So we have, I used it already a couple of times. So on C of G, we have the hard state H. H, lowercase h, yes, thank you. So we can perform the GNS representation, right? And obtain the Hilbert space L2 of G. And then we also have the representation of C of G on this space. And then if you want to have an analog of the regular representation, which is just acts by translation, typically on L2 of G, it will be the representation on this space. Okay, so definition is assume that C of G is represented on some Hilbert space. Okay, and then define maybe a map on L2 of G tensor H0, a map W via F. So this is a GNS space, right? So we have this cyclic vector which I like to denote by omega. Then we get a dense subspace by acting on omega by operators. So A will be in C of G. And then we have some other vector psi in H0. And this by definition will be, we apply the co-multiplication. So this will be in C of G tensor C of G. So it acts both on L2 of G and on H0 by assumption, right? So we apply this to omega tensor psi. So this is definition slash, yes? Psi is just a vector in H0. So psi is just a vector in H0. Yeah, and A is in C of G. This is W. Yeah, conventions, right? Yeah. Okay, then extends to a unitary map, right? Because so far we define it on a dense subset. Okay. Do a piece of chalk. And it's a unitary representation of G. No, this chalk is not good. So what it means, so first of all, we have an operator defined on the dense subspace of L2 of G tensor H naught. So we want to show that it extends, and it's actually a unitary map. And then to show that it's a unitary representation, it means two things. I mean, it has to belong to the subspace, right? To this Hist algebra, and it has to satisfy the property of the representation, right? So it has to interact nicely with the coproduct. So I will not really give the proof. I will perform some computations, maybe suggesting why it's a unitary map, but not give the other steps. So part of the proof. Okay, so we want to show that it's a so we want to show that it's a unitary map, so we want to show that it's an isometry that is onto. Right, so first we'll show that it's in isometry. So we look at W acting on some of the operators of the form AI omega tensor psi I. Compute the norm squared. So this is by definition the same as the norm of delta of AI omega tensor psi I squared. Okay, so now we just write the norm squared as the inner product. So this is sum over now two indices. For the inner product, we have delta AJ star AI omega tensor psi I omega tensor psi j. Right, because so we had this delta of AJ star on the right side, but we used the fact that this delta is a star homomorphism, so we moved it to the other side of the inner product. And now we see that we have this inner product with omega on the first leg of this tensor, right? And omega was the GNS vector for the Haar state of our compact quantum group G. So it means that this thing is equal to H tensor identity star. So this is now in C of G, and then it acts on psi j, psi I, psi j. Okay, but now we use the invariance of the Haar state. It means that H tensor identity compulsive delta is just is the same as applying H to the element and then multiplying it by the unit. So this is equal to sum ij H of AI star, okay, psi I, psi j, which is equal now to the the inner product of AI. Sorry, I swapped the j's with i's, right? That's why I was confused. So it's AI omega tensor psi I which are the original vectors, right? So this shows that that W is isometric. And then to show unitarity, you need to know that the image is dense. But the image, I need to move. Yeah, this board when I put it higher. So why is the image dense? Well, we have W on A omega tensor say B psi. I mean, we can act on psi by some other element is delta of A so 1 tensor B on omega tensor psi, right? Psi is any vector, omega is a cyclic vector. and these things are dense in C of G, tensor C of G. Okay, and then so we get basically anything in the first leg of C of G, so we can spread omega to any vector, to a dense subspace, and then psi was already any vector, so we don't really even have to care about that. So we use the cancellation rules to obtain the density. And the other parts of the proof are slightly more complicated, so I will not redo that. Yes.
So did you say W is the right regular or left regular?
Right regular. Yeah, so now maybe that's a good place to write it. So what happens for classical groups? So for classical groups, so we view C of G inside B of L2 of G. Right, so now our H0 space is also L2 of G. We don't need this auxiliary Hilbert space. So then we have W on A omega tensor B omega is delta A 1 tensor B acting on omega tensor omega. Okay, but now this thing is a function of two variables. And what's the function? I mean, this is the co-multiplication, so we have A of ST, where S is the first variable, T is the second variable, and we have B on the second variable, acting on the unit vector. Right, so this is just one, constant function 1. Okay, so then imagine that it was even a finite group, and for B, you take the delta function at some point t, then it means that you shift A by this variable t exactly. So it's really a right regular representation. It's really analogous. So maybe that's why maybe you prefer the W star, because it's just a matter of a choice of a convention.
Just one more time. Strictly speaking, you should involve the GNS representation in the formulas, right?
Yes, that's true. Yes, I should, but that would be too much notation, I think. Yeah, that's correct. Yes, in principle you should, but I just skipped this. So in principle, every I here should be like pi of AI, but. I mean, I'm already proud of myself because I even kept omega, which I almost never do. So, so that's already, I think, an achievement. Okay, so let's say we have this one very important example of an infinite dimensional representation in general, and we want to relate it to this finite dimensional representation theory, right? Okay. So it will somehow consist of two main statements. First of all, the first statement is like the analog of the Fetter-Weil theorem, that any unitary representation of a compact group decomposes into irreducible representations, and finite dimensional irreducible representations, like all irreducibles are finite dimensional. And the second statement that is also important is that all irreducible representations appear in the decomposition of the right regular. Right, so the theorem, the first part of the statement is that any unitary representation of G decomposes as a direct sum of finite dimensional irreducible representation. So the idea of the proof is once again to use our favorite tool. I mean, it seems like we only have two tools, like use the cancellation rules and use the averaging trick with respect to the hard state, and that's good. So the idea is as following. So take S to be a compact operator, and then consider, let's do it like a map, so E of S would be identity tensor H. So a unitary distribution, so yeah, we need a name. Let's call it U. So we write U star, or yeah, that's okay. U star of okay, so by definition, this thing belongs to compact operators tensor C of G, right? Because S tensor 1 is in compact operators C of G, and U star and U are in the multiply algebra. So if you multiply them, you land in K of H tensor C of G. So when you slice the right leg, you land in compact operators. So S is a compact operator. That's the first important thing. And then, yeah, as always, it's also a morphism, an intertwiner of U. Right? Because we average in such a way that we get U. Okay, so then if it's compact, then say S was self-adjoint, or we can do S positive. So if S is a positive operator, then E of S is also positive. Right, because this is just conjugating by unitary and applying a positive functional. So then, if you have a compact operator positive, so you can diagonalize it, and it will have finite dimensional eigenspaces. And the projections onto the eigenspaces will give you some finite dimensional sub-representations. So now there is one slight thing to note, that we don't know, in principle, E of S can always be 0, right? This is not that clear. Okay, so why is, or maybe why can E of S be non-zero? Okay, so the idea is to take a sequence Si, which is Pi, projection onto the subspace spanned by first n basis vectors. So this will be a finite dimensional projection of, maybe if n should be the same letter. So this will be finite rank projections converging in, say, strong topology to identity. And then you can show that because of that, this E of S somehow also converges to something nice. Somehow it's continuous with respect to some finite topology, and it will also converge to somehow will become non-degenerate at some point. And this is somehow how, using these things, you get a non-zero E of S. And then once you have one non-trivial invariant subspace, finite dimensional, And of course, you go to the orthogonal complement, do the same trick, so forth. So you can decompose into finite dimensional subspaces. And then Mike already explained how you can decompose finite dimensional ones into finite dimensional irreducible ones. So this also shows that all irreducible representations are finite dimensional, right? Because for any representation, we can find an intertwiner somehow which has finite rank. So it means that if it was irreducible, it had to be finite dimensional. So this is the main idea. And then, yeah, maybe just before a quick, yes, a question.
How do you know that you will get everything? But in principle, like if I keep the same two dimensions, so if I keep taking off some parts, it's not automatically guaranteed that.
No, this is, once you can start the procedure, it's just like a Zorn lemma. You just take a maximal decomposition. And the thing is that you can start the procedure, so it's okay, it will work.
Didn't you need some kind of non-degeneracy of this algebra of compacts intersected with?
Yeah, something like that. But this is roughly, this is roughly the idea. Yeah, that somehow you need this. You get these projections.
If you have this non-degeneracy, it says you have, in some sense, enough.
Yeah. So then, yeah. The one thing that I only want to talk about without writing anything down is that why do you get all the irreducibles inside? Well, there's this one thing that I haven't mentioned. So you can show relatively easily once you can do all the technical steps showing that W is an actual representation, that the coefficients of W are actually dense in COG. Maybe that's coefficients of W are dense in COG, and this is, you can do somehow fairly explicitly. So then W decomposes into these finite dimensional representations. So imagine that one of the irreducible somehow does not appear in this decomposition. Okay, but then this is dense, and we had the orthogonality relations. So you would get somehow, all the elements would be orthogonal to coefficients of W, but coefficients of W are dense. So it means that all the coefficients of this other representation would have to be 0. And so somehow we're using implicitly the fact that, for example, that C of G is dense in L2 of G, which is like the same proof as in the, this is like by definition basically here, right? When we do the GNS.
Did you say what you mean by coefficients?
No. So it means that you have these, so things of the form omega of identity W where omega is a functional on the compact. So basically, it's the same definition in a way. You just take two vectors and form a coefficient. Yeah. So in a way, yeah. And this is just maybe a more analytic way to write it down, but basically it's all spanned by finite dimensional things. Okay, so now I don't know what I explained, what I have not explained. Yeah. So once again, just W decomposes into finite dimensional irreducibles, and the coefficients of W are dense, also in L2 of G. So if one of the irreducibles does not appear in decomposition, it would be by orthogonality relations orthogonal to this dense subspace, so they all have to be 0. Yeah. So all the irreducibles appear in the composition of W, and actually you can check that each of them appears with some multiplicity equal to the dimension of the Hilbert space that they act on, which is like, this is something extra, which is the same statement as for classical compact groups. So it would be nice if actually this theory allowed duality, right? So you can construct this dual group. And as I mentioned there in the first lecture, somehow the role of the Fourier transform in the Abelian case is taken over by the regular representation, roughly. And then like this dual object is like the group algebra of your original thing. So we'll do some Fourier analysis now on compact quantum groups. Find a piece of chalk. Good. Okay, so as I mentioned, the most important thing about Fourier transform is that it maps convolutions to the usual products. So we need to define convolutions, right? So classically, convolution is a thing that, of course, in the analysis class you define it for functions first, but the actual definition is that you define it for measures, and then functions are viewed as densities with respect to the Lebesgue measure. So somehow that's like the actual thing that's happening. So we will define it for functionals first. So imagine, so take omega 1, omega 2, bounded functionals on C of G. Then we define the convolution to be, you first do delta, then do omega 1 tensor omega 2, and you compose with delta, right? So this goes from C of G to C of G tensor C of G, and then you slice both legs with functionals, so it goes, so this expression goes from C of G to C, and it's a nice bounded function. Okay, so we have convolution, then the second step will be to have the Fourier transform. So as I said, Fourier transform is roughly the regular representation. So it will take an element, say a functional on C of G, and it will result in element in the group algebra. So I will now write down the formula and discuss how it relates to the regular representation. Fourier transform is a map from, say, functionals on C of G into the L infinity direct sum. So we take all the sequences of bounded norm. We index over equivalence classes of irreducible representations of G, and then take the corresponding matrix algebra of the dimension of the representation. And then what's the map? So F applied to some functional omega, and say evaluate the coefficient alpha. It is by definition, you take your representation U alpha, you take the star, right? So this is an element in MD alpha tensor C of G, and then you want to get a matrix MD alpha, so we need to slice with the functional on C of G, which is exactly the omega. Okay, so now there are also these two conventions you can see in the literature. Either you have the star here or not. So this is the more like Fourier analytic convention where you have the star. And sometimes people also write without the star. And somehow both theory work, but you have to be aware that there might be some slight differences. Okay, and how does this relate to the right regular representation? I mean, as I said, the right regular representation decomposes into all the irreducibles of G. So this is basically, the algebra, von Neumann algebra, because it's an infinite direct sum, generated by the image of the right regular representation. So that's somehow the connection. But somehow, we don't have to actually don't have to know it, but somehow if you want to have these classical theorems from Fourier analysis, for example, that if the Fourier transform is 0, then the original element was 0, then you would need to use this faithfulness of the regularization at some point. Okay, so the thing we want to check is that actually it maps convolutions to products. This form of convolution of two functionals. Sorry, omega. This is not by definition, this is just the statement. So it reverses the order because we have this star here. But it's not a quantum thing. So if you do Fourier analysis on classical compact groups, it's the same formula. It also reverses the order. So let's maybe, so this is maybe the one computation that we can do. So we want to look at this. So we evaluated it at alpha and we apply the definition. So we have the identity tensor omega 1 convolves with omega 2 applied to U alpha star. Right, this is by definition, you write down the definition of the convolution, so it's identity tensor omega 1 tensor omega 2, and you apply it to delta of U alpha star. Okay, now U alpha was representation, so it somehow interacts nicely with the delta.
Yes, that's ID delta.
Yeah. Yeah. Small ID. Okay, so the next step is that we have identity tensor omega 1 tensor omega 2. So we use this definition, so we have that this is U12 alpha, U13 alpha star by the definition of a representation. So now the star reverses the order, so we have identity tensor omega 1 tensor omega 2 on U13 star U12 star star. Okay, so now only omega 2 acts on the third leg and the omega 1 acts on the second leg. So this is how we get this reversion of the order. So this is really f of omega 2 times f of omega 1. Okay, so as I said, in the classical case, so this object would be like the group algebra of G. Like classically, this is what it is for a classical compact group, and morally, it's the same for compact quantum groups, and we can just define this object to somehow to be this thing. These are the things formed from the I wrote left regular, but you can do equally right regular. It's some version of the group algebra. Okay, so now it makes sense to say how this direct sum relates to the dual discrete quantum group. So we write define this object infinity of gamma to be this direct sum. And we want to show that this is some sort of quantum group. So we want to define a co-multiplication and maybe some extra structure. It's like similar to the classical case, right? When we look at the group algebra, I mean, it's classically it's exactly the functions on the dual group, so it should be some sort of group type object. And we, in the group algebra case, we define the co-multiplication, the antipode, and things like that. So we also want to define the co-multiplication in this case. We'll actually write the formulas for Hall measures and things like that. But before that, I need to write something more about the right regular representation. So for any compact quantum group G, we can consider the space L infinity of G. So Mike already mentioned that somehow there are different algebras with which we can describe the same quantum group. He mentioned this reduced version, which is like the closure inside the GNS representation of the Hall state. He mentioned the universal one, which is like the universal enveloping system algebra of the Hofstadter algebra. And there's also a von Neumann algebraic version. So this is like the related to what Mike said is you take a look at the reduced one. So this sits inside B of L2 of G, and you take the bicommutant. So you take the von Neumann algebra generated by this reduced algebra. So this is like the analog of the, essentially bounded functions on your group. It has a measure, so everything is nice. And then what I want to claim is that somehow we define representations on the level of somehow using the C of G, but you can also somehow define them using this L infinity of G, and it's slightly more useful for me right now. And you can make sense of the statement that W belongs to L infinity of gamma tensor L infinity of G. The von Neumann tensor product. So once you somehow believe that you can change C of G to this thing on the right leg, this is not too bad, because this only just comes from the fact that you can decompose this right regular representation into finite dimensional representation. So that's how you get these finite dimensional matrix algebras. And then to define the co-multiplication, so there is a unique delta gamma.
Sorry, so that W is meant to be some form of right regular?
Yeah, so this is the same W that we had. Yes, questions. Jacek, maybe first.
So formally you also should write pi back to the second back of W to back to the previous definition.
Yes. Yeah?
Is there an informal way you can write W explicitly in that algebra, like as direct sum of all the years?
Yeah. So yeah, informally it's like this. Yeah, I write it here. Informally you can write sum over alpha, and then you take the coefficients. So we take the matrix units in this D by D is this D alpha by D alpha matrix algebra, and tensor with the matrix coefficients of this representation, and you sum over, alpha, ij, something like that. So this really lives in the any sort of nice algebra that defines your compact quantum group, and this lives in the finite-dimensional blocks here. So there's a unique map such that you will define this using the right regular, so that delta gamma tensor identity applied to W is equal to W23, W13. So at least on a formal level, this equation makes sense, and somehow this equation has a unique solution, and delta gamma will be a co-multiplication, it will be co-associative, and it's like the analog of the statement that that delta gamma on lambda g or rho g, because we're in the right regular, rho g. So now the quantum analog of this definition of co-multiplication for group algebras. But this, of course, we cannot really write because everything is pointless. Yes.
What tensor product are you considering?
The same one. The fundamental tensor product. If fundamental algebras, no fancy tensor products. So for C-star algebras, the minimal one. For fundamental algebras, the usual one. The only reasonable one. Okay, and then we can write the Haar measures. So unlike the compact case, there in general will be two. Unlike the classical case, where the discrete groups, they are unimodular, they have only one Haar measure. The formula, so there is like the right Haar measure will be this thing where x alpha is the component in d alpha, and we assume that x in this direct sum is finitely supported, because this is just like for an infinite discrete group. I mean, the measure is infinite, so it's not really defined on any map, but for finitely supported things, it's well defined, so it's formally a weight. And then we take x finitely supported, and then x alpha will be the alpha component of x. So we have this formula. So this will be the right Haar measure, and h alpha, hl of x will be very similar. Trace rho alpha, trace rho alpha inverse x alpha.
That's on the little L infinity.
When it's a weight only to L infinity of gamma, Sorry, formally on this algebraic direct sum. But it's like a nice weight on the infinite direct sum as well. So we can write, for example, the counit as well. So the epsilon of x is a certain component of x. So there are you have all the irreducible representations to choose from, and there's one particular one which is the trivial representation, right? Which is a one-dimensional representation, and you take this component. So this is x triv. So this is one-dimensional representation, so this is an actual number, right? This will be the co-unit. Okay, so yeah, there is a way to define a quantum group structure on this dual object. And maybe in the last, I think 20 minutes. That's quite good. We will say a bit more about the Fourier transform. For example, in some cases you can actually compute the formula for the Fourier transform, so that's quite nice. And then, just like classically, I mean, the Fourier transform is a thing that you can define on different function spaces, right? You define it maybe typically first on L1 or on the measures, but you can also define it on L2 by extension, things like that. And the nice thing that we all know is that on L2 it's an actual unitary operator. So this is maybe something that I want to discuss in these last 20 minutes. So what we basically do now is to write the formula for a Fourier transform of a coefficient of some irreducible representation. Okay, so what's important that, as I mentioned, we define the Fourier transform on functionals, right? So if we want to define on elements, we need to view them as densities with respect to the Haar measure. Okay, so view x is phi of g as a functional where you put it as a density inside the Haar state. Okay, and then, so now take something particular, so take x to be equal to some xij, eij alpha. Right, so I pick one representation alpha, one irreducible alpha, and I take the, uij alpha, and I take coefficients of this particular representation, and then the Fourier transform, I used f, Fourier transform of x at pi. So I only get something non-zero if pi is the same as alpha, equivalent to alpha. So delta alpha pi, and then the rest is you get 1 over the quantum dimension of alpha. Take the x transpose rho alpha inverse. Right, so x is just the scalar matrix with entries xij. And this is the real reason why I prefer to work with this definition where you have a star. That actually this is somehow, if you start from a particular representation, you get coefficients in this representation, not in the conjugate one. So this is maybe better for recovery in Fourier analysis. I think we have some time for the proof. extension I want to keep. Proof. What happens is that, okay, x, so the Fourier transform of x evaluated at pi. Okay, so first of all, it's linear, so we can definitely write, xij, take the coefficients. Then we view this x as a functional respect to h. So then we have h. You have uij alpha here. Right, and then you take the coefficient of pi, so we have u lk pi star, and then you have the e l k l. Right, this is the star, so you have the star of the element and the transpose in the middle. Okay, I guess that's fine. That's the same that I wrote in my notes, so I assume it's correct. Okay, so then the first thing which follows from the orthogonality relations is that if pi is not equivalent to alpha, this expression is 0, right? So we get the sum is over all these I, j, k, l. So this is delta alpha phi. Once again, sum of x, I, j, h of, and now we just write that this u alpha lk star uij alpha. Okay, and now we just use the orthogonality relations to evaluate this thing. Okay, so this is this formula. So we need we will have this 1 over the quantum dimension like we wanted. We want the second indices to be the same. So we get delta alpha pi over the quantum dimension of alpha. We have delta kj, right? We want the second indices to be the same. X, I, j. And then we get row inverse evaluated at the ki entry. So we get row inverse IL KL alpha. Okay, so we erase this and just write that K is J. And now Xij, this is the Ji entry of the transpose. So this is the X transpose Ji. Okay, and now if we sum over I, we get the JL entry of X transpose row inverse. And then we sum over all the coefficients, so we get the result. Okay. So for this here, the class of functions that we care about the most, these matrix coefficients of finite dimensional representations, we really know how to compute the Fourier transform explicitly. And now we can use this computation to show that when we choose a particular inner product on the range, that this is actually a unitary map. As always, I need more chalk. I think there will not be any chalk left for anyone after during talk after me. what's already clear somehow from this statement is that in the image you get all matrix units in any, in any matrix block in our decomposition in L infinity of gamma. Right? Because this is a finite expression, and you can get, if you take, X transpose to be, rho alpha times some matrix unit, you obtain this matrix unit as the image. So all the matrix units in the image you get, and then whatever Hilbert space structure you can imagine on the image, this will be dense. So checking, once we define properly what we mean by the unitarity of this Fourier transform, checking that the image is dense will be the easy part. It's already visible here, so we'll only have to check that it preserves the inner products. Okay, so then we can define L2 of gamma to be the GNS space of L infinity of gamma constructed using the right Harweight. So we didn't really explain the GNS, Robin didn't explain the GNS representation for weights as opposed to states, but it's somehow the same as the classical case. It's easier to do L2 spaces for probability measures, but you can do them for sigma finite measures, and it's roughly the same construction, but you somehow have to, instead of having the whole algebra acting on your Hilbert space, you need to restrict to some dense subalgebra on which the weight is defined, and then you take the completion. So it's roughly, especially here somehow, when this is just a direct sum of matrix algebras, just restrict to the algebraic direct sum, finite things, and on them you define inner product, and then you complete it. So did I erase the formula for the right Harweight, right? So I need. So the HR X, because we'll need it, is the sum over the irreducibles, trace rho alpha, x alpha. And then the statement is that f, say, extends to a unitary between L2 of G and L2 gamma. Which, the word extends should be taken with a grain of salt, because it doesn't really, it's not really an extension. We first have to do restriction to the dense thing and then extend, but just like in the classical analysis, right? On R, when you do L1 to L2, it's not really an extension, but some people call it that way. Right? Okay, so what will be sufficient to check? To check the isometry property on matrix elements. And then by sesquilinearity, we'll extend it to finite sums of matrix coefficients, and then by density we'll extend. Right, so we do this. We have the inner product of Uij alpha UKL pi is equal to H of Uij alpha star UKL pi, which is by the orthogonality relations delta alpha pi over the quantum dimension of alpha delta JL rho inverse Ki. Okay, so this is the computation on the compact side. Then we know that the Fourier transform of Uij alpha is equal to Ej alpha over the quantum dimension of alpha and rho alpha inverse. So we compute the inner product of these. We have the inner product of Ej alpha inverse ELK pi over the quantum dimension once again of pi. Okay, so now it's easy to see, I mean, these are matrix units, possibly different blocks. Then if alpha is not pi, then this is 0. So this is delta alpha pi over the quantum dimension of alpha squared, and we get this definition. So we have trace of rho alpha times trace of rho alpha. We get the adjoint of this, which is rho alpha inverse Eij alpha. We get ELK alpha rho alpha inverse. Which is delta alpha pi over the dimension. So this is the quantum dimension as well. The trace of rho alpha, so we get rid of the square, and then here this thing cancels. We get from this delta JL, right? Because otherwise the matrix units will multiply to 0, and then we have the trace of EIK alpha rho alpha inverse, which is the Ki entry of this rho alpha inverse. Somehow it works in the end, but there's plenty of choices you have to make along the way, so that works somehow. There are different choices you can make that still make it work, but see, I mean, one of the things was that I had to view element of x in C of G as a functional, so I have two choices, right? I can view it as a density on the right or on the left. Then on the gamma, I can choose either the right Hard weight or left Hard weight. So in general, I have like 4 choices. And then it's not clear like which choices work, which choices do not work, but you have to choose a convention and somehow follow it, and it will work out in the end. Okay, with a minute to spare, I think I will thank you for your attention.
We have a couple minutes for questions.
Yes?
So you were able to write down a co-unit. Can you write down a nice antipode, or is that still hopeless also in this case?
I think you can write the antipode on the finite thing, but it's you don't have a nice formula. Like for the compact case, you had a nice formula that on the matrix elements, right? That S of Uij is Uji star. You don't have a nice formula anymore. Do you, right? Or I?
There is quite a nice formula. So you just have to kind of remember this idea, how is the antipode on a dual Hopf algebra defined? So it's just composing with S and taking a star.
Yeah.
So you just write it, and I think you'll get a reasonable formula.
Yeah, I guess. Yeah, maybe that's. Yeah, we'll get some formula. That's true. Yeah.
Did you swap a rho for a delta? I'm comparing the bottom two equations.
Uh,
Dare to say. Yes. Step by
matter.
That's the correct statement. Yeah.
So for Ontarian dual or compact people group would be a discrete group. Should I think of the affinity of gamma as a discrete quantum group?
Yeah, exactly. It's like it should be a discrete quantum group, yes.
And is there, I mean, if you try to do this, I don't know if this even exists for non-compact quantum groups?
Yes. There's like a duality for locally compact groups, but it's somehow the theory is much more complicated technically.
But for example, I mean, here you see that if you take the center of this von Neumann
Yes.
that's just a discrete space. Would that
Yes.
change if you do this with non-compact stuff?
Yeah. It will not be. There will not be. There will be nothing discrete somehow about it. Yeah. Yeah. Just like for R. Yeah. For R as well. Yeah. It's really special. Yeah. And you can also like. All of the discrete quantum groups appear as duals of compact quantum groups, so that's why I wrote the definition like that. But you can axiomatize also like what it means to be an abstract discrete quantum group. You can write it, and then, which is actually close to this. It means that its algebra is like this discrete, direct sum of matrices, and like you have extra axioms. But then there is a general theory for locally compact quantum groups, but it's much more technical. But duality also somehow uses this multiplicative unitarist, I mean, these operators W and things like that. But also defining them is much more technical.
Let's start the break, and we can ask more questions informally during the break. So, thank you.